Hi everyone. So this is going to be the video for Chapter 7, Lecture 1. So Chapter 7 is on thermochemistry. And just, if you break down that word, thermo means heat, right? So heat chemistry. So in chemistry, it's really important to be able to track energy exchanges, or AKA heat exchanges, right? Because that's oftentimes tells us a lot about the reaction, right? And how to optimize the reaction, right? So thermochemistry is a very important aspect of chemistry. So you may have used hand warmers before, and if you have, then you have experience with thermochemistry. The way that most hand warmers work is it has iron filings inside, and when you activate it, the iron filings react with oxygen, and it's a redox reaction, right? So the iron gets oxidized, oxygen gets reduced, and it turns into iron 3 oxide, basically the rusting of iron. So not only does the iron rust, but it also gives off heat. So we call this type of reaction exothermic. X meaning out, heat out. So since the heat comes out of the reaction and our hands are there, right? Our hands benefit from the heat that comes out of the reaction, right? So we do love exothermic reaction when we're cold, right? Because it's going to warm us up. So combustion reactions are like that too, right? Why do we burn firewood when we get cold? Well, that combustion reaction releases heat and therefore warms us if we are around that, right? So the amount your hand temperature rises depends on several factors. It will depend on the size of the hand warmer, right? So of course, the bigger the hand warmer, the warmer your hands are gonna get. But also the size of your glove, right? So if you have really big glove, then of course a lot of the heat's gonna get lost to the glove and it won't heat your hand up as much, right? So um, the amount of heat that's released by the reaction, right, is going to heat the surrounding. Okay, that's that's why we like exothermic reactions, right? Okay, let's talk about the nature of energy. So heat is a type of energy, right? But let's go, zoom out just the nature of energy in general. Remember, energy is defined as anything that has the capacity to do work. And then remember, we defined work earlier as force times distance, right? And then heat. What is heat? Heat is the flow of energy caused by a difference in temperature, right? So remember that the first law of thermodynamics says energy can neither be um, created or destroyed, but it can be exchanged between two objects when they come into contact and they have a difference in temperature, right? And the way that heat flows is always from where there's more heat to where there's less heat. So you can think of energy as a quantity an object that can possess, right? Just there's a value, right, of energy that an object will possess. And that's by way of, the mass, right? How much material is made up of, right? How much matter is inside. Um, so me, for example, I have an energy number, and so do you, right? Depending on, how massive we are. Do we eat breakfast, right? There's an energy number there, right? And now you can think of heat and work as two different ways an object can exchange energy. Um, so I can exchange energy through work, right? Which is what I'm doing right now, which I'm being animated and I'm expending energy, right? But I'm also expending energy through heat. So if you come and stand close to me, you can feel that I am giving off heat, right? So any object um, is can, right, exchange energy in those two different ways, right? Either work or heat. And heat can flow in or out of me, right? And work can be done by me or can be done on me as well, right? So it can go in either direction, right? Okay, now remember we had classified energy before into two types, kinetic and potential. So kinetic energy is the energy of motion, So anything that's associated motion, we call that kinetic energy, right? And that's really easy to see that, you know, things that are in motion carry energy. Pretty easy to conceptualize that, well, if a ball is going to be thrown at my head at a high speed, I better dodge, right? Because that ball is carrying energy. Thermal energy is also a form of kinetic energy, but it's associated with temperature. So thermal energy is the vibration of the molecules on the molecular level. How fast they vibrate, right, is that thermal energy. And then when you take a thermometer, right, and you touch it to that thing, that's basically what the thermometer is measuring, is how fast those molecules are vibrating, right? And so that's what thermal energy is. And it's a form of kinetic, right? Because vibration is still a motion. Okay, the other form of energy, right? Potential energy, that's the energy that is stored in an object, or the energy associated with the composition of an object, right? So here's position, right? So gravitational energy is stored when you pick up a ball and lift it in the air, right? And the higher that you lift it in the air, the more gravitational potential energy that you store. Because then if you drop the ball from a higher altitude, right, it's going to fall and cause more damage than if you drop it from a lower height, right? Because it's storing more energy. Okay. So potential energy is not in motion, right? It's being stored. But when you let the ball go, this potential energy transfers to kinetic energy. Um, and as it falls, kinetic energy increases and potential energy decreases. Right. And there's another type of potential energy, right? It says energy that's associated with composition or position of the object. So composition, right, means the energy that's stored in the bonds of each compound. So you guys heard of TNT, right? Which is trinitrotoluene. And within the bonds, right, you store a certain amount of energy. And so um, if TNT is disturbed, basically that energy gets released and you have an explosion, right? Where that energy gets released. And where's that energy from? It's from the bonds, right? That is associated with TNT. And that's what we call chemical energy, actually, right? Is the potential energy due to the structure of the atoms and how they're attached to each other, the atoms' positions relative to each other, and all those things, right? So there's chemical energy that's stored in everything, right? And that potential energy could be released, right? Under the right circumstances, right? Okay. So the manifestations of energy. Here's the flow chart, right? So energy is defined as the capacity to do work, and it can be categorized in two types, right? Kinetic, which is energy due to motion, and potential energy, which is due to position or composition. Now, under kinetic energy, you can have thermal energy. That's the energy associated with temperature, right? And the vibration of molecules. And then there's chemical energy. Um, Underneath potential energy, and that's energy associated with the positions of electrons and nuclei within the atoms of the molecules. Okay, so here we go. The law of conservation of energy, aka the first law of thermodynamics, states that energy cannot be created or destroyed. When energy is transferred between objects, or convert from one form to another, the total amount of energy is always constant. Okay. So you can't lose energy, you can't gain it. It can only get transferred. So in this picture here, it illustrates that, right? The spring acts as a way to store energy, right? So you can push down on the spring, and obviously you're doing the work to push down on the spring. So now the energy is stored in that system of spring and ball, right? And the harder you push on that system of spring and ball, the more energy that you store there, right? That's why it takes work for you to do that. As soon as you let go, what you're doing is you're transferring that potential energy into kinetic. And how high ball goes is an indicator of how much potential energy was stored in that spring ball system, right? So the more you push down and the more energy you store, the higher the ball is going to go, right? Because energy cannot be created or destroyed, right? So the more potential energy you have, the more kinetic energy you can get, you can transfer to, right? Okay, so in this chapter, since we are uh, uh, interested in following energy, we have to kind of set a reference point. And we do that with a couple of vocab terms. First, we define what is the system. So the system is basically our reference point, our frame of reference. And the system is what you're studying. It's usually the reaction, right? The reaction is the system, and then everything else around it is the surroundings, right? So whatever it is that you're studying, that's becomes the main player, that's the system. And then outside of that is the surrounding. When you set those boundaries, then you're able to, say things like, is energy going out of the system or into the system? Or vice versa, is the energy going out of the surrounding or into the surrounding? And so you have a frame of reference in order to talk about energy exchange. Right? So here's an example, right? We all know like our gas gauge, right? We can think of our gas gauge as an energy gauge too, right? So if you have, in this top left picture here, before this energy transfer, the system energy gauge is half full, right? And the surroundings energy gauge is a quarter full, right? Now, the after picture is that the system's energy decreased, right? Decreased by how much? One quarter. Okay. So that means the surroundings energy gains must be gained by one quarter, right? Because energy cannot be created or destroyed. So in other words, whatever energy is gained or lost by the system, then the surroundings has to do the opposite, right? So if the system loses energy, it must have lost it to the surrounding. So the surrounding gains the energy, right? In the same amount, and vice versa. If the system gained energy, then it must have gained it from the surrounding. And so the surrounding will lose energy by the same amount, right? So it's conserved, energy is conserved, right? Which is really good. When we know that law, we can really simplify the math, right? We don't have to guess, oh, where did that energy go? Um, we know that it has to come from somewhere, right? Okay, so now let's talk about the units of energy. Okay. And let's go to the board for this. So energy, units of energy, we can derive from the kinetic energy equation. So KE, kinetic energy, is 1/2 mass times velocity squared. And then all we have to do is figure out what are the units for mass and velocity, and we'll figure out what is the units for kinetic energy. So mass, right? Remember the base unit for mass, SI base unit, is kilogram. Okay. And then velocity. Well, you guys know velocity. Velocity is like um like your car, right? When you drive your car, it tells you 60 miles per hour, right? It's telling you a distance over some time. Okay. So miles per hour is not SI base unit though. What would it be for SI base unit? Meters, right? Because that's a distance, right? Over time, the time is the second SI base unit, right? So now you square that though, and so this is what you get. Kilogram times the quantity meter per second squared. So that makes the units of energy as kilograms meter squared per second squared. Okay. And since this is a mouthful to say, we've decided to just call it 1 joule. Okay. So 1 joule is 1 kilogram meters square per second squared. So that's why, when you're doing calculations with energy, um, things should be in kilogram, meters, and second. Okay. All right. So what is that? Um, so 1 joule, right, is 1 kilogram meters per second squared. Um, uh, how much is a joule? Well, a light bulb would be 3.6 times 10 to the fifth joules, or 0.10 kilowatt hour. Okay, so a joule is also a Newton meter, right? Because remember, work is force times distance. So work is an energy unit as well. So work can be measured in joule, but since work is force times distance, force is in Newton and distance is meter. So 1 joule is also equal to one Newton meter. Okay. Another energy unit that you guys actually already know, the calorie. Right, we measure food in calorie. Actually, we measure food in kilocalorie. Kilocalorie is 1,000 calories, and it's represented by a capital C. Okay, so these are the food calories that we talk about. Like 2,000 calories um, in our daily diet, right? Uh, that would be actually 2,000 kilocalories. Okay. So a calorie, what is it? It's the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay. So it's telling you how much energy you need to put in there to take 1 gram of water up by 1 degree Celsius. Here are some energy conversion factors that you should know. 1 calorie is 4.184 joules. Right. 1 big calorie, right, with the big C, is actually 1,000 little calories, right? So a kcal or kilocalorie would be 4,184 joules, right? And then a kilowatt hour is equal to 3.60 times 10 to the 6 joules. Again, you don't have to memorize these conversion factors, right? They're on your conversion factor sheets. You just have to know how to use it. Okay, so let's go back to the first law of thermo, which is the law of conservation of energy. Okay. So what is thermodynamics? Thermo again means heat, right? Dynamics is movement. So thermodynamics is the study of energy and its interconversions, or basically the exchange of energy, right? How does energy move? Um, so using the law of conservation of energy, we can actually track how energy moves because we know it can never be created or destroyed. So again, right? That what that means is the energy of the universe can never change, right? That means the change in energy of the universe must be equal to zero. Okay. And since the change in energy of the universe is the change in energy of the system plus the change in energy of the surrounding, both of these have to add each other to be equal to zero. Right? So in the end, what you get is that the change in energy of the system must be equal to the negative change in energy of the surrounding. Um, Otherwise, meaning whatever is happening to the system, the opposite is happening to the surrounding, right? So pretty easy um, concept there, right? So again, back to that energy gauge, right? Look at the top figure. Before energy transfer, the system has half, right? And the surrounding has a quarter. After energy transfer, you see, the system went down to a quarter. So even if you didn't see this picture here, you should know that the surrounding energy must have gained the quarter that the system lost. So the surrounding is now half, right? Okay, so let's talk about internal energy. Right? Internal energy is the sum of all the kinetic and potential energies of all particles that compose the system. Okay. So internal energy you can think of as a number, right? A number that Every single object has. Um, so, if you look at your chair, right? Um, the sum, the internal energy there would be the sum of all the kinetic and potential energies. Well, your chair's not moving, so kinetic energy would be zero, except for the vibration, right, of the molecules within the chair, which is the thermal energy, right? So a tiny bit of that is kinetic, and then most of it is potential energy, right? In the form of the molecules that make up the chair, all the material that make up the chair. Those are all potential energies, right? And so if you add that up plus the thermal energy, you get internal energy, right? So each object has its own number. You can even like analyze yourself. Your internal energy would be, all your mass, your heart is beating, right? So that's kinetic energy. Your stomach's digesting, so that's kinetic energy. And then you add all the potential energy, right? Which would be like all your cells, everything that is the chemical makeup, right, of you. So that would be your internal energy. Okay, so the change in internal energy of a system depends only on the amount of energy in the system at the beginning and the end. Okay. So this is what is called a state function. So the state function is a mathematical function whose result depends only on the initial and final conditions, not on the process used. So a state function, a good analogy would be like your bank account. Okay. So let's say at the start of the month, your bank account is at $1,000. Okay. And then at the end of the month, your account is $500. So what is final minus initial? 500 minus 1,000 is negative 500. So that would be a net change, right, of um, $500 loss, isn't it? Right? It doesn't matter that maybe you could have become a millionaires two or three times during the month. Who knows? Maybe, mid-month you became a millionaire, but then you spent it all, and you spent all that money. So it really doesn't matter what happens within the month. We only care about the final and the initial state, right? So measuring change in energy, we don't really care about what's going on. We only care about the initial and final conditions, right? Not the process. Um, Here's another example of a state function. Right. So you have this mountain path, right? Two mountain paths, path A and path B. Path A is this zigzag, kind of windy, 12 miles long, all the way to the top. And then path B is very short, like 5 miles, and you just go straight up to the top. Okay. Now, the question is, path A or path B, which would cost you more energy to take? Think about that for a second. Would path A or path B, you know, cost you more energy? It's kind of a trick question. Both paths will cost you the same amount of energy. You know why? Because both paths takes you from 0 to 10,000 feet. Remember, it does not matter the process. It's only final minus initial. It's a displacement of 10,000 feet vertical. You will spend the same amount of energy. And now you're like, well, how's that possible? I mean, like I feel like, I wouldn't be as tired if I took the windy road. And I'm like, yeah, it's true. You would not be expending as much energy per time, but you have to go longer, don't you? You have to go 12 miles, right? Whereas in path B, you go just 5 miles, but you go straight up. So you're spending a lot more energy per time, right? Um, so therefore it works out, right, to be equal. Okay. So that's how energy works, right? Energy transfer. They're all state functions. And realizing that will allow us to also simplify the math later on as well. Okay, so let's go to the board for this one. I'm going to show you guys energy diagrams, but I don't like these as much. So I'm going to show you guys how you should do them. Okay, so let's take the reaction that we had. Carbon solid plus O2 gas goes to CO2 gas. Okay, so we have um, reactants and products, right? Now, on the reactant side, remember we were talking about internal energy, okay? So let's say carbon had some amount of internal energy, and you add it to O2's amount of internal energy. So in your energy diagram, all you need to draw is the y-axis is energy going up, and you're going to draw a horizontal line for the reactants. Okay, so that would be where their internal energy is, right? Some arbitrary value. Now, CO2, if you take its energy measurement, right, it lies here. Okay, so CO2 lies lower in energy than the reactants, and you can connect it with this kind of curve here, this slope. Okay. We'll talk about more what this is later, especially in Chem 2. But basically, when you have reactants going to product, you always need to have some sort of activation barrier, right? You need a spark to get up to the top before it can go to the product. Okay, so don't worry about what that is for now. Um, just draw it like that though, because that's actually the way that you draw energy diagram. So the main thing that you want to see here is that CO2 lies lower in energy than carbon and oxygen, which means the system must have lost energy, right? The change in energy here is negative, right? Because a lower number subtract a higher number, right? So the delta E here is less than zero, okay? But what if I was to, flip this around? CO2 gas goes to carbon solid plus O2 gas. Well, since I flipped this around, CO2 is now here, right? So CO2 was here, and CnO2 was up here. So now we have this graph, right? Where this is CO2, this is CnO2. So here our delta E is a positive number, right? The change in energy, because the system, right, went from a lower energy to a higher energy state. So energy must have flowed into the system, and therefore you have a positive energy change, right? Greater than zero. A higher energy number subtract a lower energy number is positive, okay? So that's how you always do it. When you see delta, guys, delta means change, okay? And delta, you always take the final minus initial, okay? So if it's delta E, you take E final minus E initial, right? That's how you find the difference of something, right? Final minus initial. All right. Okay, so now let's talk about energy flow, right? All right. So remember, we define the system and the surrounding. The system, usually always your reaction, right? Whatever the reaction is, that's called the system. And then we can measure the energy flow. Is energy going out of the system or into the system? And, and they're indicators. Like for example, you burn wood, right? Energy is flowing out of the system because you are the surrounding. The wood burning is the system, and you feel hot, so you're the surrounding. That means you're receiving energy, which means the system, right? The combustion process of burning the wood is losing the heat. Okay. So when energy flows out of the system, it must flow into the surrounding, right? So here we've, designated the blue part is the system and the yellow part is the surrounding. So whatever is lost from the system must go to the surrounding. So the surrounding absorbs that same amount, right? So if delta E is negative for the system, it has to be positive for the surrounding, and vice versa, right? Due to the first law of thermodynamics, energy cannot be created or destroyed, and vice versa, right? If the surrounding loses heat, so delta E is negative for surrounding, then the system must gain it. So delta E must be positive. Okay. All right. So the energy diagrams that I've showed you guys, that's how I want you guys to do it. And now these energy diagrams are very simplistic. Um, so please use the one that I just showed you. All right. Now let's talk about energy exchange. Remember, energy can be exchanged in two ways, either through work or heat, right? So my example before, I'm working right now, right? I'm walking around, I'm talking, I'm writing down things. I'm definitely losing energy, right? I'll get hungry pretty soon here, right? And then I'm also losing energy through heat, right? So my body is just giving off heat, right? And you can feel that. So even if I stop moving, eventually I'll still be hungry because I'm losing energy through heat. Okay. So those are really the only two ways to exchange energy. It makes things super simple. So when you analyze a system, all you need to do is analyze the work and the heat, add those together, and you have the total change in energy of the entire system. Does that make sense? All right. So the equation is very simple. The change in energy, right, total of a system is equal to Q, which is heat, plus W, which is work. All right. So here's a new symbol for you, right? Probably you haven't seen Q before. Q means heat. Okay. From now on, when you see that, Q means heat or thermal energy. Now Q and W, they have signs, right? Because we are talking about energy flow, aren't we? So there needs to be a from and a to, or a loss and a gain, right? And those come with symbols, with signs. So let's talk about the sign conventions for Q, W, and delta E. Q is heat, right? So if the system gains thermal energy, it will have a positive sign. If the system loses thermal energy, it'll have a negative sign. So really simple, right? Not anything you have to think hard about, right? Plus means gain, minus means lose, right? Think back to your bank account. It's the same way, right? Gain, lose, plus or minus. W, work, same way. If work is done on the system, then the system gains work, right? It's a positive sign. If work is done by the system, so if I'm the system, I'm doing work right now, right? Because I'm like talking and all that. So I'm losing, right? I'm losing energy through work. So work is negative. Now, when you add Q and W together, your delta E can also be positive or negative. So if your delta E is positive, that's a total net gain of energy into the system. Or if the delta E is negative, then you have a total net energy outflow, right? Uh, uh, of the system. Makes sense, right? It's quite intuitive. Right? Here's a nice graphic, right? That shows you the energy exchange between system and surrounding through work and through heat. And that's it. Right? Okay, so let's take a very simple um, phenomenon, and we're going to analyze the heat and work uh, to figure out the total energy change. So let's do like the billiard ball colliding with each other. So here, let's say we have a very smooth pool table. The initial kinetic energy of the cue ball is 5 joules, right? So it's gonna go and it's gonna hit the purple ball. And notice that the purple ball is gonna go away at 4.5 kilojoules, right, of kinetic energy. The white ball stops. So that means its kinetic energy is 0. Okay. But the purple ball only goes away at 4.5 joules. Well, wait a minute. I started with 5. How come I only have 4.5? That means that half of it was lost through heat. Okay. So we can analyze it like this. The work was done by the white ball, right? If the white ball is our system here, right? So you have to define the point of reference. So the white ball is the system. So the white ball does negative 4.5 joules of work, right? Because it does work on the purple ball, right? It pushes the purple ball away at negative 4.5 joules, and it lost its heat of half joule. So Q is also negative, negative 0.5 joules. So now when you add Q and W together, your delta E is negative 5.0 joules, right? So that's why the Q ball here is kinetic energy of zero, right? At the end, it lost everything, right? It lost all 5 joules of energy. 4.5 of it through 4.5 of it through work, and 0.5 of it through heat. All right, let's go to the rough pool table. So now you have a rougher pool table. The white ball strikes the purple ball. The purple ball goes slower, goes away slower, and only 2 joules of kinetic energy. So that means that 3 joules was lost to the table. So now W is negative 2, right? So the white ball only did 2 joules of work, so negative 2. The white ball now lost 3 joules of heat, so that's negative 3. So delta E is negative 2 plus negative 3, which is negative 5. Again, you have conservation of energy, right? But they're partitioned different, aren't they? In the smooth pool table, the cue ball was able to do more work and lost less heat, right? But at the end of the day, what happens? It's the same. The total energy that the white ball um, lost was 5, right? Okay, so let's do this example problem. A potato cannon provides a good example of heat and work associated with a chemical reaction. In a potato cannon, a potato is stuffed into a long cylinder that is capped on one end and open at the other. Some kind of fuel is introduced under the potato at the capped end, usually through a small hole, and ignited. The potato shoots out of the cannon, sometimes flying hundreds of feet, and the cannon emits heat to the surroundings. If the burning of the fuel performs 855 joules of work on the potato and produces 1422 joules of heat, what is delta E for the burning of the fuel? Okay, so in these types of problems, the first thing I always do is figure out what the system is, right? That's what you always do. Figure out what the system is so that you can talk about the energy exchange, okay? Where is it coming from? Where is it going from? So remember, the system is always the reaction, okay? So in this potato cannon, what is the reaction? And there are a lot of words in here, right? But you have to be able to learn how to pick it out. And here's the key word, the burning of the fuel. That's the chemical reaction, right, guys? What type of reaction is that? Combustion. Okay. So once you know that, right, that's the system. Now it's going to be easier for you to assign um, the signs, right, for Q and W. So we know that delta E, right, delta E is equal to Q plus W. And it says the burning of fuel performs 855 joules of work. So for work, it's 855. And if it performs work, guys, is 855, should it be positive or negative? It does the work, right? So it's negative. Okay. And now let's figure out Q. Q says it produces 1422 joules of heat. So 1422. And now we have to figure out the sign of that, right? So read it again. It says produces 1422 joules of heat. That means it lost, right? Lost heat. So that's a negative as well. Okay. So guys, what is delta E? Minus 422 minus 855. That's minus, it looks like, what, 77, 22, 77 joules, right? Unit of energy there. Okay. So do you see it's not complicated if you define the system correctly, right? So here's what happens when you if you define it wrongly? What if you said the potato? Because you're like, oh, the potato is it's the thing that's shooting out of the cannon. Let's call the potato the main character, right? Like it's got to be the system, right? Because it's the main character. No, the potato is actually the surrounding. Because what's affecting the potato? What's causing it to fly out of the cannon? It's the combustion, right? The burning of the fuel. Okay. So if you had picked potato as your system, that would have, you know, led you the wrong way. Okay. And so that's why, um, I always say you want to correctly pick your system first before you um, solve a problem. Okay, let's talk about heat exchange. Okay. Now, some people get heat and temperature confused, so let's clear that up. Okay. What's the difference between the two? Heat is the exchange of thermal energy between a system and surrounding. So heat exchange occurs when the system and surrounding have a difference in temperature, and the heat, the basically heat will go from where there's more heat to where there's less heat until both the system and the surrounding has equilibrated to the same temperature, right? And so then what's temperature? Temperature is just the measurement of the thermal motion of that sample of matter, right? So on the atomic scale, what is the vibration of those molecules? That's what the thermometer is measuring, and it gives you a number, right? A temperature. So of course, the higher the temperature, the faster those molecules are vibrating, right? So heat will always flow from high temperature to low temperature, no matter what, until both objects reach the same temperature. Okay, so we can actually measure how much heat is absorbed, um, or how much heat is needed in order to raise the temperature of something. And it's through this equation here. Q is heat, okay, is equal to C, and we call this the heat capacity. And that's always in joules per Kelvin or joules per Celsius, and then times delta T. Okay. So this basic equation is just telling you, all right, if I want to um, change the temperature of something by a certain amount of degrees, then I need to add this much heat to it. Okay, that makes sense, right? So the more heat I add, the higher the temperature will go. They are in direct relationship with each other, right? But then whatever the material I'm trying to heat will have its own intrinsic constant called the heat capacity, aka, some things heat much easier than other things. And you guys have experienced with this in real life, right? Like you put things in the microwave and they don't heat evenly, right? Some things will heat faster than other things, even though they're subjected to the same heat environment, right? So some things will just absorb heat better than others, and the temperature will change faster, right? So we call um, you know, things that heat slower high heat capacity, right? So that means it can store so much heat before its temperature changes. But then there's other things that like barely you just give it some heat and the temperature rises. So those things have low heat capacity, right? So that's what a heat capacity is, right? So the heat capacity of something de depends on its material, right? And you can look those up so you never have to um, memorize it. But it measures the substance's intrinsic ability to absorb heat. We call this the specific heat capacity because it also is measured as, 1 gram. Okay, so the specific heat capacity is the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And it's denoted as C little s. Okay, and the units are joules per gram per degree Celsius, right? Um, Sometimes molar heat capacity is used. So instead of grams here, you're going to have moles. So it'll be joules per mole per degree Celsius, right? So again, guys, specific heat capacity, the amount of heat energy required to raise the temperature of 1 gram of that substance by 1 degree Celsius. So if you look at this table, by far, The highest heat capacity is belonging to water. Okay. Water has one of the highest heat capacity of all compounds. Um, so 4.18, what does that mean? It will take 4.18 joules of energy to heat 1 gram of water uh, to to raise its temperature by 1 degree Celsius. And then you see the other elements, they're much lower, right? So something that you know quite well, like some aluminum, right? If you put aluminum foil, compared to water, aluminum heats up and cools down really quickly, doesn't it? Right? And so that's why we use it to wrap our foods in and to use it to heat, because it heats up and cools down fairly quickly, right? But then there are other things like lead and gold, they have even lower heat capacity, right? So again, it's just intrinsic to that substance, right? Whatever its heat capacity is. Okay, so now we have a better equation even to measure how much heat it takes to heat up a certain mass of a compound by a certain temperature, by a certain degree, right? Or you could even think about it as cooling, right? How much energy do you have to take away to decrease the temperature of something, and here is its mass, right? So the equation is Q is equal to MC delta T. And this equation is on your equation sheet, so you don't have to memorize it. You just want to make sure that you know how to work with it. So remember how specific heat of water was so high at 4.18 joules per degree Celsius per gram. Um, this is what um, this is why our the weather around the Bay Area is quite temperate, right? So San Francisco, for example, it never gets really, really hot, right, or really, really cold, and that's due to it being surrounded by water. So cities that are surrounded by water, what happens is when the rays come down, right, the water absorbs a lot of that um, uh, sunlight, and it takes a lot more to heat up the water. And so cities that are surrounded by water tend to stay cooler, right? But when you go inland and all you have is asphalt and the sun rays are shining down, it's just the asphalt. It has a way lower heat capacity that's absorbing those rays, and all of a sudden you have a rise in temperature and it's a lot hotter, right? And so that's why coastal towns, right? Coastal cities have much temperate environment than inland cities. Okay, let's do this problem together so we can see how we use Q is equal to MC delta T. It says, suppose you find a penny minted before 1982 when pennies were almost entirely copper in the snow. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is negative 8.0 degrees Celsius, to the temperature of your body, 37.0 degrees Celsius, assuming the penny is pure copper and has a mass of 3.10 grams. All right, so again, write all this on the board, and then we practice. So we have copper penny, 3.10 grams, pure copper penny, and it says how much heat is absorbed when the penny goes from negative 8 degrees Celsius to your body temperature, 37.0 degrees Celsius. Which heat, which is Q, is absorbed. All right. So let's do it. We know the equation is Q is equal to MC delta T. So the mass is 3.10 grams. then we have to go back to that table and look up the specific heat of copper. And you'll see that it's 0.385 joules per grams per degree Celsius times delta T. So remember, guys, every time you see delta, it's always final minus initial. Okay. So delta T is T final minus T initial. So you have to look in the problem and see, okay, what is the final temperature and what was the initial? Use the language, right? It will tell you from here to there, right? From -8 degrees Celsius to 37. That means 37 is your final and -8 is your initial. Okay. And be careful here, right? Because you're doing 37 minus the initial, but the initial is negative. So it's minus a negative, right? So inside here is actually 45, right? That's the change in temperature, right? You warmed it up by 45 degrees. So what is Q? Should get 53.7 joules. Okay. And here, let's figure out how the sig fig works, right? You have addition in here, so it goes by decimal places. That's 45.0 degrees Celsius, right? Because it's to the first decimal place. So that's 3 sig figs. This is 3 sig figs. This is 3 sig figs. So you round to 3 sig figs. Okay. All right. Let's go on to the next topic here. Thermal energy transfer. All right. So when you got two objects at different temperatures and they're placed in contact with each other, the heat will flow from where it's hotter to where it's colder, always. Okay. Until when? Until they reach the exact same temperature, right? You guys have had experience with this. So you can write a very simple equation, right? The Q, the heat of the system, is equal to negative the heat of the surrounding, right? That's the energy transfer. So if you have, say, a block of metal that's hot, let's say that's your system, right? It's gonna lose heat to the water, which is considered the surrounding. So Q of the metal is equal to negative Q of the water. Okay, that's that thermal energy transfer, right? And so now you can expand that out, right? Q metal is equal to negative Q water. Q metal is what? MC delta T of the metal. So the mass of the metal times the specific heat of the metal times the change in temperature of the metal is equal to negative Q water, which is negative mass of the water times the specific heat of the water times the change in temperature of the water, right? So let's do that for this example. A 32.5 gram cube of aluminum, initially at 45.8 degrees Celsius, is submerged into 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? Assume that the aluminum and the water are thermally isolated from everything else. Okay, so let me write this down. We have a 32.5 gram cube. Initially, so T initially, TI, I stands for initial, 45.8 degrees Celsius, is submerged into 105.3 grams of water. At initial temperature, its TI is also 15, is 15.4 degrees Celsius. Okay, so they both have initial temperatures that are different, right? The cube is hot, 45.8 degrees Celsius. The water is colder at 15, and it's asking for what is the final temperature. Okay. So why doesn't it say what is the final temperature of water and cube? Well, because they're both going to be at the same temperature, right? Once they equilibrate. So what you're doing, you're dropping a hot cube into water, right? And so the cube will decrease its temperature. The water will increase its temperature until they're at the same temperature. And that's what it's asking us. What is the final temperature? Okay, so again, we have to write Q metal is equal to Q negative Q of the water, right? Because whatever is happening to the metal, the heat that's lost by the metal is gained by the water and vice versa, right? And so they just need to have opposite signs. Then you can expand this out, right? Q is equal to mc delta T. So it'll be mass of the metal. And our metal is what? Does it tell us our metal? Yes, it does. It tells us that it is aluminum. Okay, so mass of the aluminum times specific heat of the aluminum times delta T. And at this point for delta T, I'm going to expand it out as T final minus T initial, right? Because I need to solve for T final. So T final minus T initial is equal to negative mass of the water times the specific heat of the water times water's T final minus T initial. Okay. And then remember, we're solving for T final. Okay. So let's plug in everything that we know. We're going to use the table for specific heat. Okay. So the mass of the aluminum is 32.5 grams. And we're going to multiply by the specific heat, which of aluminum, which is 0.903 joules per gram per degree Celsius times T final minus the T initial of the cube is 45.8 is equal to negative, the mass of the water is 105.3, okay, times the specific heat of water. And this, at this point, you can see that the units cancel and you just have joules left, right? Because we have degrees Celsius here. So I'm going to just leave out the units because it's really cumbersome at this point. And we're just going to do the algebra first, okay? So let me just rewrite it without the units so that the algebra is going to be easier. So specific heat of the aluminum, 0.903 times T final minus 45.8 is equal to minus 105.3 for the mass of the water. Specific heat of water is 4.18 times 4.18 times T final minus initial temperature of water is 15.4. Okay, so algebra, guys, right? We have everything except for TF, and all we have to do is solve for TF. So I have to get TF by itself. What I would do first is multiply these two numbers together, right? So I will have 32.5 times 0.903, so 29.35 times TF minus 45.8 is equal to, and then I'll multiply these two together, 105.3 times 4.18. It's negative 440.15 times TF minus 15.4. Okay, now at this point, what I can do is, um, yeah, I can divide by 29.35 to each side so that I just get TF minus 45.8 is equal to, I'm going to divide 29.35 over here, right? So I'll take this number divided by 29.35, and I'll get negative 14.997 times TF minus 15.4. Okay. All right. So at this point, what I want to do is I'll leave the left side the same. And on the right side, I'm going to multiply through, right? I'm going to multiply through. So negative 14.997 TF plus 230.95. Okay? You guys following, right? Yeah, in fact, you should just pause the video. Just try to figure out TF for yourself, right? Test your algebra here and then check your answer. All right, so at this point now, um, I'm going to collect the terms together. So I'm going to add TF to this side, and I'm going to add 45.8 to that side. Okay, so adding 14.9 to this side, now I'll have, that's 1 TF plus this. So that's 15.997 TF is equal to, and I'm going to add 45.8, 230.95 plus 45.8, 276.75. Then solving for TF, I'll divide by 15.997 to both sides. And I'll have 17.3. And that would be in degrees Celsius, right? Now, does that make sense, guys? If you look at the problem, the metals started at 45.8 degrees. The water was 15. So the metal did cool, and then the water did warm up to 17, right? But the final temperature was closer to water's temperature than to aluminum's temperature. But I think that makes perfect sense, don't you? Because water has a much higher heat capacity than aluminum. So of course the final temperature is going to settle closer to water, right? Because it takes so much more heat to heat up water, right? To actually change its temperature. It takes so much more energy to actually change the temperature of the water. So you just have 17.3, right? Of course, the final temperature should lie in between the two initial temperatures. Okay. So if you guys need to, go back, brush up on your algebra as usual, right? But that's basically for these types of problems, these heat problems, or problems pertaining to this chapter. This is probably the hardest that you're going to come across as far as algebra, right? So just practice that. All right, so that's it for today's lecture, everyone. I'll see you next time to finish up chapter 7.